So good afternoon, good evening. We are welcome back going on Chapter 9, Regression Wisdom. Now, in this chapter, we're going to talk a little bit more about correlation, regression, and how we can interpret it. And sometimes we be careful in how we interpret it. We have to look carefully at pattern changes and how the regression is going to be affected by different points of data. We're going to talk about the dangers of extrapolation, the effects of outliers, leverage, and influential points. The problem of regression of summary data and the mistake of inference causation or inferring causation. So first thing is, let's have this table to the right. It gives me a number of seniors who graduated from a high school during the latter half of the last century. Data was not available for all of the years, especially some of the years that were longer ago. So first I want to do is pause the video, use this data to make a scatter plot, and describe the trends you see in the data. Not just the overall trend, but there are multiple trends. So pause the video, load this in, and let's plot that scatter plot and see what we come up with. So at this point, if you're playing video again, you must have already got it all typed in there. So I plot that in. I plot my scatter plot. It looks like this. Now, of course, this is not a complete scatter plot. I have to label my axes. My year graduate is the year I'm using to make my predictions based off of, which makes sense. The number of graduates I have from year to year is probably going to remain somewhat stable, but the number of graduates I have doesn't really work to predict what year I must be in. It doesn't really work the other way around. So this would be a completed scatter plot. Now, if I look at this, and I'm going to make my associations appear to be pretty strong. Those points are not far away from each other on the y-axis. However, it increased in a linear fashion from 1950 to about the 70s. Then it began to decrease, again, in a linear fashion to about 1990. Then it started going up again in 2000. And that was the last year I had any data on. Now, there could be all kinds of reasons for this. And honestly, if I was gathering data, those points are probably something I'd want to investigate. I want to know, why did I reverse course? Oh, let's go back to that. I might want to know, why did it start decreasing? It's just being difficult today. I might want to know why I started decreasing and why I started increasing again. So that gives me something I want to go back to investigate further. But overall, I know it was linear from 1950 to the mid-70s. Then it's linear decreasing to about 1990. And then it was linear increasing again. Those are what I can say about the trends. Next thing I want to say is, it doesn't show how many students graduated in 1969. So instead I want to come up with a model to use it to estimate the size of that class. What years would I use and why? So think about that for a minute. We've got our model. We've got our scatter plot, I should say. We want to develop a model to make a prediction about 1969. So I only want to use some of the data. Okay? I don't use all of it. I'm using data from when it was at first section, when it was still kind of linear. It was linear increasing. 1969 is going to fall right about here. So that's right in the edges of that linear data. That's probably all I'd want to use. Because the data over here, well, that's not really reflecting what's going on in the late 60s. It's the data from the late 60s that shows me what's going on in the late 60s. So I might use the data from 1950 to 1976. And that would just look like this. A lot fewer points. But it's in the data range I'm looking for. 1969, right around here. Using that data, running my linear regression, StatCalc 8, I get the number of graduates. My prediction for the number of graduates is equal to negative 27,739 plus 14.3246 times the year. That will tell me how many graduates I'm predicting there to have been in 1969. If I plug 9, and before I really want to use this model, I want to know, is my model good enough? Do I have a good enough model? To find that out, I have to see my predictions. Look at my residuals. Now, if I look at this, my residuals, there's no clear pattern in those residuals. That looks like a good model. It's appropriate for me to use a linear model because the residuals of my linear model don't have any clear pattern. And the next question is, how good is my model? That's that R squared. How much variability did we account for? Well, we account for 95.6% using that information from linear regression. 95.6% of variability of graduates can be explained by the year according to this model. So my estimate for 1969, I need to use my model. I plug in 1969 for the year. And I found out there would have been about 466 graduates. That's my estimate using that model. Different models give me maybe different estimate. Now, let's say I want to project the graduating class size all the way through the year 2005. Well, think about what kind of model would we use then? Okay, so I'll look at my data and figure out what I want to use to make a prediction about the year 2005. Well, as we recall, our scatter plot was linear increasing, then linear decreasing, then linear increasing again. I want data about 2005. I don't need the data from back in the 1950s. In fact, that's when it was increasing. Then it started decreasing. Then it started increasing. I want the most current data that's still probably going to affect the trend I see. So only the current data. Using that data, I come up with this kind of scatter plot. And that would be my model using this data. So the number of predicted graduates is equal to negative 15,859.9 plus 8.1 times the year. My residuals, no clear pattern residuals. Of course, I don't have a lot of data in there though. But the residuals tell me it's okay to use a linear model. It's nice and random, no clear pattern. And I account for 90.7% of variability according to this model. My R squared is 0.907. 90.7% of variability in graduates can be explained by the year using this model. And according to this model, I'm going to get 494 graduates in 2005. Now, there is some aspects of the data that should cause me to be cautious about this prediction. So go ahead, think about what we've got. Look at that data. What could cause me to be a little cautious in how strongly I want to make that prediction? Well, if you remember, only 6 points of data in there, and I'm extrapolating. I'm making an estimate or a prediction based on something that's outside the range of my data. Anytime I'm extrapolating, I need to be less confident in that prediction. So I'm going to be a little bit more cautious in this. My prediction's 5 years into the future. I'm trying to make predictions about the future. That can be a dangerous proposition. So I'm going to be a little cautious on that. Extrapolation. Sorry about that phone ring. Extrapolation. All we're going to talk about extrapolation is when I use my least square regression line to predict values outside the domain of the explanatory variable used to create that line. So what I'm saying is, I'm looking for those points where the data I need to make a prediction about my x value is a value for x that's outside of the previous x's I've had to deal with. It's outside the domain of my explanatory variable I use to make the line. Outliers. Oh, even if friends warn G, be careful about regulating and extrapolating. Outliers. It's a data point that has high leverage. We're going to talk about leverage. And whose residual lies outside the overall pattern of residuals. There's a little bit more to it, but that kind of gives us our main focus about it. And if I'm talking about just univariate data, a single variable data, it can be an outlier in the x direction, or in the y direction, or both directions. High leverage. This is a data point whose x value is far from the mean of the x values. It's kind of a subjective term. So what's far away mean? Well, it's far away. It's subjective. Some points will seem far, other points won't seem far. It also has to do with how much data we already have. The more data we have, it's a little bit harder for a point to have leverage. But, briefly, leverage means the x value of the data point is far from the existing x values. It's far from the mean of the x values. Farther out you go, the more leverage you have. So if I want to pick up the other side of teeter-totter, my little skinny blue person, red stick figure red head stick figure needs to be further away to get more leverage. Think about Spider-Man, some of the early Spider-Man movies. She had some leverage over Peter Parker. You know, further out you go on a ledge, the more leverage you have. So it has the potential to change the regression line. Sometimes it'll strengthen the relationship by increasing the correlation and the determination, the R squared. So a point with high leverage can increase or strengthen the relationship by inflating the correlation or the R squared. So let's see how we can use this. I could have a point that's wandering around. We're going to do something, a little exercise called the wandering point. First thing to do is we're going to do these 4 points to begin with. The point 1, 2, 2, 6, 4, 2, 5, 6. So what you need to do, catch your calculator, and you need to load those 4 points in the calculator. So if you look, I've already taken a moment. I have those 4 points in mind. I want to run stat, calc, 8, and save the line, vars, yvars, y1. So we'll save the equation, and we can look at it. Second stat plot. And our plot is turned on. It's set for scatter plot. It's set for L1, L2. So it says zoom 9. And that's what we have. That's my scatter plot with line of least squares for those 4 points of data. Now, we're going to have the power of the wandering point. We're going to see what a wandering point can do. We ran our linear regression. Our R was 0.3162. My y hat, my predictive value, my line of least squares, my linear model was y hat equals 2.8 plus 0.4 times x. Now we can investigate the power 1 point can have on correlation and slope. So first one I put in is 3, 4. So I'll put my calculator again. And we're going to add the point 3, 4. So I go stat, edit, and I go over to my x's and come down to the bottom and tell it 3. Then we come over and tell it 4. And we rerun the linear regression in order to find out the power of this wandering point. So stat, calc, 8, and I need to resave the line. Vars, yvars, 1, y1. Now I've got my new correlation. My new correlation is 0.3162. My new slope, 0.4. So 0.3162, slope is 0.4, and now I plot the line. If I plot the line, this is what it looks like. I want to figure out my residual. How far away from my line of least fit, line of best fit, is this new point? That new point's right there in the middle. It's on the line, so it looks like 0. I have no residual for that point. Now I got to ask myself, did it have leverage? To have leverage, I say, where is this point, this new point, compared to the mean of the x values? Well, it's right in the middle of them. So it's not far away at all, so it doesn't have any leverage. Next thing, did it have influence? Well, slope's 0.4. It was 0.4 to begin with. It didn't change anything. That means it didn't have any influence. So it's not influential. Now I have a 0.86. So that point has moved. So I go in my stat, edit, and I change 3, 4 to be 8, 6. So I come down 3, change that to an 8. And we change 4 to be a 6. We rerun our regression. Stat, calc, 8, and we save our line. Vars, yvars, function, y1. And we've got my new R. My new R is 0.5. My slope is still 0.4. If I plot it, this is what I look like. I look at my residual. Again, that point, this point is on the line. So it doesn't look like it's having any residual. So leverage. How far is it on the x's? Well, it's way out here. It's far to the right compared to the other ones. It has some type of leverage, but it didn't change its slope. So it's not influential. So let's try another point. Let's move that point again. It's wandering around. So now I'll try 10, 7. So it moved, even if that line didn't look like it moved too much. I'm going to do stat, edit, I'm going to change it 10, 7. And then we rerun our regression. And of course, saving our line. So I've got a new R of 0.6156541214. Okay, I'm going to use like the first four. 0.6157. My new slope, 0.422, well, 0.4228. If I want to see this, we've already seen our thing before. We've resaved it, so I just zoom 9. And that is exactly what I have over here. So it hasn't changed much. Correlation, our correlation changed. It actually increased quite a bit. Went to 0.61 from 0.31. Slope of our line is now 0.4228. But look at my residual. It's pretty small. It might be on the line, but I can't tell if it's exactly 0, but it might be on the line. So it's at least small compared to the other residuals. The distance from the line for this point is small compared to this point, this point, this point, or the first point. So the residual is small. Look, leverage, compare it to my other x values. It's 10. The other one's maxed out at 5. So yes, it has leverage. It's far along on the x-axis. Also want to know, does it have influence? Did I change my slope? Well, my slope started off as 0.4, now it's 0.42. Some people might say, well, technically it changed it, so I'm going to say it had influence. I'm going to say that slope really didn't change. I don't think it has much influence. It's not really influential, but it did have leverage. Leverage just cares about position. Leverage doesn't care about what it does, just about position. So he tries for 3.8. So you go ahead and try it. Pause the video, come back, we'll talk about 3.8. Okay, so if you put that in, new correlation, 0.3357. Slope, 0.4. Residual, I look at my picture again. Now I look at this point, it's pretty far away from the line compared to the other points. So yeah, that has a large residual. What else do I want to say? Is it influential? Well, it's right in the middle of all the x's. So no, I'm sorry, is it leverage? It's right in the middle of all the x's. It doesn't have any leverage. Influential? Well, slope's still 0.4, so no. No leverage, no change in slope. It's not influential. Try 1.7. Okay, so if you got me back, if you still need to pause it, if you haven't finished, pause it and then come back. Okay. So if I look at it, correlation just changed. It actually became negative. So that's a significant change. In fact, if my correlation is negative, then my slope has to be negative. So my slope went from 0.4 to negative 0.06. And it has a medium-sized residual. So does it have leverage? It changed things, so does it have leverage? Well, no. Leverage only cares where is it related to the other x value. So this one has no leverage. But is it influential? Yes. It has influence. It did change the slope, so it does have influence. Try again. 8.9. How does 8.9 do when that point is changed to 8.9? What do we see? So pause the video, finish it up. All right, so you're back. Correlation, 0.73. Slope, 0.8. Size of the residual. Looks like size of the residual is pretty small. But that correlation went through a significant change. That slope went from 0.4 to 0.8. So it definitely had some influence, but how about leverage? Yes, it's far away from the other points, so it does have leverage. It did make a slight change slope. Now, I didn't think it's a big change in correlation. It is influential. Try it again. 10.0. In fact, just looking at the scatter plot, we should already have some answers. Right? Our correlation we came into, negative 0.4888. Slope, negative 0.3740. Look at our residual, small, maybe medium, small. Yeah. Leverage, definitely. Very far away from the other x's. And influence, clearly. Very change in the slope, change in the correlation, definitely influential. I mean, take all that data, put it together, and we notice we can look at our influential points in the scatter plot. We look for points that departed from the overall pattern. Those that were outliers tended to be influential points. Okay. Now, do not just look at the size of the residual. As you can tell, not all of these points that had large residuals, just because they had large residuals they ended up a lot of times being influential, but not every time. We had a large residual for 0.38, but the slope was 0.4. That's not influential. Slope didn't change, but I had a large residual. So we cannot just look at the size of residual to decide if it's influential. Originally, we only had 4 points. Well, for a moment, let's say I had 50. Now I put all 50 in kind of the same spot. Okay. And then I want to see a point, a 51st point, what would happen for it to be influential? Well, if we have 50 points all in the same spot, all in the same area, that 51st point is probably not going to be very influential because it has to break the pattern that 50 points have made. Okay? It's easy to break a pattern that 4 points make. But a pattern made up from 50 points already? No. It'd have to be significantly different. So how could I change that 1 point? Well, to have as much influence as 10, 0, that point would be much further along the x-axis. Maybe it would have to be 100 instead of being 10, 0. Okay? Now again, we can't throw data away. So what I do is I have my scatter plot, I look at it, I've run my regression. If there's a couple points on there that I think are influential, well, I take that point off and I rerun it. And then I can see, was that point influential? I can decide if an outlier was actually influencing the data or not. Now, if you're still having a little bit of a rough time with this, I want you to go to page 205 of the textbook. A little example about bozo, help you out. Okay, bozo can talk to you a little bit more about it. Let's talk about lurking variables. We talk about shark attacks and ice cream, and the ice cream consumption went up, the number of shark attacks went up. We talk about that really what's going on is if it's a hot summer day, people are more likely to eat ice cream. And if it's a hot summer day, they're more likely to get in the water. That temperature is hiding in the background and causing both of those to be affected. So it's not something I actually studied, but it was having an effect. It's a lurking variable. Okay? So it affected the relationship of the variables, but it wasn't included in the variables being studied. Now, let's say I gave a vocabulary achievement test to elementary school students, and I found there's a strong association between the student's weight and their vocabulary score. What could happen that might have made that happen? What kind of explanation that might explain that? We want to talk about causality. What could explain increased weight and increased vocabulary score? Well, maybe kids who are overweight, they stay indoors and they read instead of going out and playing sports. So weight is indirectly causing a better vocabulary. Maybe that's what's going on. That's possible. It's not ridiculous. Even if it was, we'd have to study it to find out. Maybe kids who read a lot spend less time doing fitness-enhancing activities. They're not exercising, they're reading more. So it's really vocabulary might be influencing it, making it easier for them to gain weight. Neither of those consider age as a lurking variable. Older kids are bigger. They probably have better vocabularies. And there's a clear association between weight and scores on vocabulary tests if I gave it across a lot of different grade levels. So a vocabulary test that has second graders taking it and has 12th graders taking it, I expect the 12th graders to do much better, and there's a clear association now between weight and the score. Now, summary values. Correlations based on averages are usually higher than correlations based on all the numbers that make up the averages. So if I'm based on averages, my correlation tends to be higher than if I do it on the actual data. So using a single mean to represent 30 numbers, that doesn't reflect the variation between the 30 numbers. Okay? My correlation's higher if I'm using those averages, but it's not reflective of all of those points of data. So it's an important thing to remember when you're working with summary values. Lastly, absolutely super, and it's not quite lastly, but super, super important. We keep saying it. Association does not imply causation. If I have a strong association between two variables, x and y, it could be any of the following. 1, x causes y. Now remember, association doesn't imply causation, but causation could still be happening. X and Y are both responding to something else, something that's unobserved. It's called common response. That's just like the shark attacks, that air temperature. Both of those variables, ice cream consumption, shark attacks, are responding to that air temperature. It's a common response. It's a lurking variable. If I talk about freshman GPA and SAT scores, both are responding to ability and knowledge. SAT score isn't causing the GPA. GPA isn't causing the SAT score, but both of those are affected by ability and knowledge. Also, the effect of X and Y, that can be completely mixed up with some other variable. Okay? There's no way we can tease apart what's happening. We would never be able to figure out exactly what the effects of X on Y are. That's called confounding. Where it's mixed up. It's confusing, it's confounding. So X and Y are completely confused together, it's confounding variables. So soccer coach wants to improve the team's playing, so he has them run 2 miles a day. At the same time, some of the players start taking vitamins. In 2 weeks, he noticed the team's playing a lot better. But the coach and players don't know. Is it running or is it the vitamins? Those two things have been mixed together. We don't know what's causing what anymore. We've introduced confounding variables. Okay, it's confused things. We don't know what's causing what anymore. Now, confounding is always a problem, a potential problem in observational states. So I'm just watching a group. But in some experiments, I can control for it. If I have a control group and a treatment group, we're really going to talk about control and treatment groups. Okay, confounding is always a problem, always a potential problem in observational studies, but I can control for it in some experiments. And that was it. That was it for the chapter. We did the wandering point exercise. We're getting ready to start chapter 10. Start doing the review. Want to be ahead on that review and get it knocked out. I look forward to seeing you in class.